In the last video, we constructed a stiffness matrix to solve a slightly more complex problem, one involving two springs instead of just one. This idea is used with many numerical methods out there. One of the most popular numerical methods is the finite element method, used frequently for solving structural problems. We use the finite element method to do finite element analysis, or the common acronym you see for that, FEA. I'll talk about in this video a few other methods as well, the boundary element method, finite volume method. But to give the basic idea of the finite element method, we can take relatively complex structures and break them up into these simple shapes. In this case, those rectangular bars that we figured out the stiffness of. And by breaking up into many of these shapes, we can approximate the result on the entire structure, making an assemblage of these. Now, we're not limited to just using these box elements. In SOLIDWORKS Simulation, we'll find we have access to a few different element types, ones that will map to this curvature a little better. We call second order tetrahedrons. More on that later on. But the basic principle is we construct the stiffness matrix similar to the manner we did in that two-element problem. We build that matrix on this entire three-dimensional problem and then solve that matrix based on your loads, your external loads. We solve it for the displacement. So the problem looks more like this. We know your loads, you apply them, we figure out the stiffness matrix based on this assemblage, and we determine the displacements, the unknown in this equation. Now, other methods are out there for solving numerical problems. Another popular method is the finite volume method. The finite volume method is very popular in fluid dynamics tools. Our SOLIDWORKS flow simulation uses this method. The basic idea behind it is, let's take this example. Let's say it's a heat exchanger and there's fluid flowing in and out of the board through a series of tubes. And let's say there's air flowing in between these tubes. Think of it kind of like a radiator. If we take a look at just one of these tubes, and the mesh that our SOLIDWORKS flow simulation tool might use looks something like this. A grid, Cartesian grid. And if we take a look at one of these elements, let me zoom in on maybe, let's pick one, how about this guy? It looks kind of like this. But an element is a simple thing, a cell is a simple thing. It's not going to notice the curvature here. It's going to say there's a solid region here, and this is a fluid region here, including this region is also part of that fluid region. And it solves fluid dynamics equations by linking the cells together, the cell immediately adjacent to it, and adjacent to the other side. They have their own equations. And the idea is that the mass flow rate coming in has to be equal to the mass flow rate leaving. And so you see a bigger area coming in, a smaller area going out. That means the velocity has to be faster over here. Gives it a nozzling effect. So we can kind of see how we can solve for velocity by having that mass conservation principle plugged into the solver. And also the mass flow rate leaving this cell has to be equal to the mass flow rate entering this cell. So you can see we're linking the equations together. We're building sort of a mass conservation matrix in this system. So the finite volume method is very similar to the finite element method, but we're constructing these cells and looking at the fluxes entering and leaving the cells. Very popular for fluid dynamics, and our plastics flow tool uses it as well, or SOLIDWORKS plastics. And then yet another method, the boundary element method. This is one that's used exclusively by our SOLIDWORKS plastics as far as the SOLIDWORKS simulation suite goes. And the idea behind this one, if you have a thin part, thin cavity that we're going to try to fill with plastic, So the cavity is filling. Sometimes these simulations can take a while to run. If we use the finite volume method, it solves it directly the same way a flow simulation would solve it, and gives us pretty good accuracy. Compared to a simpler approach, the boundary element method is like a sort of a quick and dirty way to run it. That way, we're only going to mesh the boundary. We're not going to mesh internally. We're not going to break up this in the internal region into cells. We're just going to mesh the boundary. And then there's equations in the background that describes what plastic does in between these two boundaries. Based on the distance between the two boundary elements, it determines that's the thickness. Based on the temperature and the viscosity of the plastic material, it can determine what the flow profile and flow rate should be in this thickness region in between. So the boundary element method uses something we call shell elements inside of our SOLIDWORKS plastics tools to run flow analysis.